All right, so today we're going to review periodic trends. We're going to talk about some organic chem, get you ready for things you'll see in the future. Let's review some periodic trends. If you don't have a periodic table handy, I'll give you one of my little ones here so that you can just jot things down on your periodic table. So you can just kind of keep a running tally of our periodic trends we're learning today. Just kind of draw a generic periodic table in your notes. That works too. Okay. So let's talk about periodic trends. Now some of these we've already talked about, some of them we haven't, so that's why I call it a review. All right, let's talk about radius, the size of the atom. The radius increases down a group. Increases down a group. Now whatever you learn going this way, it's always the opposite going the other way. So if it increases down a group, so atomic radius increases going down, what's it going to do going across? It's going to be the opposite, right? It decreases across a period. Atomic radius decreases. Right? So you don't need to memorize, picometer lengths here. You can just look at your periodic trend. If I said, okay, who's bigger, sodium or argon, right? You don't need to know that one of them's got a radius of 186 picometers and one of them's got 98. You don't need to memorize that. Just know your periodic trend that going across a period, right, the radius decreases. If I said who's bigger, sodium or cesium, right, sodium and cesium are in the same group, you just know your periodic trend, 265, I don't need you to memorize the number, right? You just need to learn the periodic trend. So if you know it one way, it's the opposite going the other way, which is convenient. That's nice and convenient. All right, now what causes this is something called effective nuclear charge. And we can actually do some pretty gnarly calculations on this, which we're not, just throwing that out there. But let's at least understand where this trend comes from. Okay, so our electrons are attracted to the nucleus, right? Because they're protons hanging out in the nucleus. And they're also repelled by other electrons, right? Electrons are going to repel each other, but they're going to be attracted to the nucleus. And so the nuclear charge that any electron experiences is going to be the effect of both of those factors, right? Does this make sense? Electrons will repel each other, but they're going to be attracted to the nucleus. And so here's some pictures. This isn't from your current textbook, I don't think. I can't remember which book this is from. But let's just look at helium. Two options here. Okay. So here, there's just one electron around, right? It's just feeling an attraction to the nucleus. It's not feeling any repulsions. Whereas here, there are two electrons around, right? Because those two are repelling each other, this one's easier, or this one's easier to remove. Does this make sense when you start throwing that extra electron? Those two repel each other. So this one's going to be easier to remove, whereas this one, if there's not another one in its vicinity, it's harder to remove. So there's no repulsion. See what I'm saying? If we're looking at another one, again, one by itself versus in close proximity to each other. This one will be easier to remove than this one, again, because we've got those repulsions going on, whereas we're not having those repulsions there. And so here's some pictures to represent that. So in other words, here are the radii, right? Here's the radii if you're going across the period, right? There's the radius getting smaller, right? But the effective nuclear charge is getting bigger going across. So again, another way to think about it is you've got a more positive nucleus versus a more negative electron field, okay? And again, that's about as far as we're going to get into effective nuclear charge. You can do some calculations on it, but I'm not going to make you do it. So using your periodic table, which of the following would have the largest radius? I mean, there's no math to do here. Just look at your periodic table and figure it out. Which one's going to be biggest? Chlorine, sodium, silicon, or sulfur? Which one's biggest? First, you need to decide if they're in the same group or the same period, and then apply your trend. Who's the largest? All right, sodium's biggest. Going across going across, right? Across the period, radius decreases. Effective nuclear charge increases. Okay, what about these? Who's going to be the smallest? Apply your periodic trend here. Who's the smallest? What is the periodic trend? Let's first establish that. Going down a group, what happens to radius? It increases. So who's going to be the biggest? Right, lead's going to be the biggest. Right, increasing down a period, down a group. Now let's talk about ions. Okay, ions are different. Think about why. Cations are smaller than their parent atoms. Think about why. Think about why. You've lost an electron. Just think of it in terms of, human words. If you lose weight, most people, you're smaller, right? If you lose something, it gets smaller. Think about why. If you lose that electron, so when sodium loses an electron, becomes sodium ion, the electron cloud shrinks. It gets smaller. Right? Removing the electron pulls the atom closer together. So if you want to think about it in terms of you've got one fewer electron out there in the cloud that you're dealing with, right? So those repulsions are minimized and they can get all closer together. Does this make sense that a cation would be smaller than its parent? If you lose 50 pounds, most people are smaller than when they had 50 pounds. What do you think will happen with an anion? A monatomic ion that's an anion. It becomes bigger, right? Monatomic ions, when they are an anion, become larger, right? You've got more electrons in there now. Adding an electron or two or three, right? You're increasing the repulsions in the cloud. You're making that cloud get bigger. So an anion is bigger than its parent, and a cation is smaller than its parent. I mean, this is just kind of, I don't know, makes intuitive sense to me, right? Adding versus taking away. If you gain 50 pounds, probably look a little bigger than when you lost 50 pounds. I'm gaining some weight here. I think I look bigger. So maybe it's all in my head, but I don't think so. I think I look bigger too. Right? So we can now apply both periodic trend and we can think about ion as well. Now we've used this word already. When we were doing electron configurations, we used this word when we talked about atoms that have the same number of electrons, right? Isoelectronic means they have the same number of electrons, right? Isoelectronic means you've got the same number of electrons. So a group of ions with the same number of electrons, we say are isoelectronic. So just like when we were talking about electron configurations, right? We talked about isoelectronic then as well. Iso meaning same, so same number of electrons. So if we do this one together, right? Na plus, how many electrons is that going to have? 10. Mg2 plus, how many electrons is that going to have? 10. Aluminum ion, 10, 10, 10, 10, right? All of those have the same number of electrons. They're isoelectronic. Right, so this is what we just said. Anions are larger than their parents, and cations are smaller than their parents. So of this group of ions, which ion is the biggest? They're all +1 cations. So which one is going to be the biggest +1 cation? What's the answer? cesium, right? Which is the largest of this group. This one's a little bit tougher. We can immediately rule out which ones as not being the biggest. The two cations we can rule out, right? Because they're going to be smaller than their parents. So now we're just deciding between the two anions, which one's going to be the biggest. Well, iodide ions down here, whereas bromide is down here, right? Iodide's the biggest, 206. Do we see how we came to this conclusion? All right, let's talk about ionization energy. So this is another periodic trend we can predict from the periodic table. Okay, there are nasty calculations that can be done to calculate ionization energy, which we're not going to do. We're just talking about it from a periodic trends perspective. Okay, so the energy required to remove an electron from the ground state, that's what we're talking about when we say ionization energy. All right, so first ionization, second ionization, third ionization, fourth ionization, etc. Right, so removing the first electron, then removing another one, then another one, then another one, another one, okay? Does everyone see why we've got these little numbers after it? First ionization, removing the first electron, second, third, fourth, fifth, sixth, seventh, eighth. Obviously, when you start getting to the eighth ionization energy, that's an extremely large number. Why? Because you're into the core electrons then. And I'll show you some data to represent that. Now let's talk about what the trend is. It's requiring more energy to remove each electron. Right? So look, let's think about the electron configuration for sodium. Right? Sodium's electron configuration is Na would be, what goes in parentheses? Ne, and then what? 3s1, right? It's got one valence electron. So the energy required to remove that first valence electron is 495. Remember, these are all core. These are core, whereas these are valence. Right? So that first ionization energy is getting rid of that valence electron. Look what happens when we get to the second ionization energy. If you're trying to make Na plus 2, look how much energy that takes. Woo, that's a lot. Why? Well, because the first was getting rid of a valence electrons. This is getting rid of a core, right? A core electron is a lot harder to remove than a valence electron. Same thing happens with Mg, right? If we're doing magnesium, I don't know if I'm in the frame or not when I write right here, but oh well, we're going to do it anyway. Ne3s2, right? There are 2 valence electrons. So, I mean, those aren't small numbers, but they're small compared to the third ionization energy, right? Because you're removing the first 2 valence electrons. Okay, that's a decent number, but it's nothing compared to 7,000 to remove core electrons, right? Once you move for valence electrons, getting those core electrons costs a ton of energy. Okay, so you can see this trend. Every time you remove an electron, especially once you've removed the valence electrons and you're getting into core, the numbers are just astronomical, right? So that's why the leap happens after you removed all those valence electrons. You're getting into core. So here's the trend. It increases across a period. So you can add this to your periodic table. Ionization increases across a period, and ionization energy decreases down a group. So it's the opposite of our trend with radius. Everybody good on the trend on ionization energy? So there it is again, removing electrons, It's a different graphical representation. All right, we've already talked about electronegativity. You guys know this trend. What is the trend in electronegativity? As you're going across, what happens to electronegativity? It what? Increases, right. We talked about this one way long time ago when we were doing Lewis structures. Increases across a period and decreases down a group. Right? Fluorine's most electronegative element. We say electronegativity is a measure of how well you share electrons in covalent bonds. Right? So we already know this trend. We talked about it a long time ago. Most electronegative element, right? We're increasing across a period and decreasing down a group. So we've learned this one already. All right, so those are our trends that we're reviewing today. Radius and ionization energy are the ones that we hadn't officially talked about yet, but we've already talked about electronegativity. If you know it for growing across, then just reverse it for down a group. So that's the convenient part. If you just learn it one way, right, then you know the other way by default, by reversing. Questions from me on periodic trends? All right, so I know that's a big jump to go from periodic trends to organic, but that's okay. Let's do one more just for good measure. Rank these in decreasing size. So on your paper, take a second and rank these in decreasing size. I'll pause it for a second. All right, so we are decreasing size, which means we put the biggest one first or last. By decreasing size, biggest one goes first, right? Do we agree? All right, one more for you to try. Rank these in increasing size. And I'll pause it for you again. All right, so we've got this last one to do. Do we agree? Increasing size means smallest one goes first. Do we agree? All right, we'll just skip that one. Let's talk about functional groups, which you may or may not have done in high school. So this is something that if you're taking elementary organic, it'll help you get ready for that. If you're taking full organic, it'll obviously help you get ready for that. But just let's pause for a minute, have a sentimental moment, because this is our last new topic we're covering this semester, and it has no math. So if you need tissues, you know, for your crying, you can come get one. It'll be okay, I promise. All right, so this is just a preview. Just a little preview, all right? Something to whet your appetite for maybe taking elementary organic. No math in that class either. Woo-hoo. Be offered next semester. You can take both elementary organic and Chem 2 at the same time. So I teach both classes, and obviously I can't teach them both at the same time, so they won't conflict. Just a little preview of that. And if you like this, you might think about, maybe I should go take elementary organic. First half of the semester is intro to organic. Second half of the semester is intro to biochem. And all the biochem stuff probably did in biology, because it's like transcription, translation, and carbohydrates and proteins and all that stuff. All right, so organic chemistry, enough advertising mercilessly, right, is the chemistry of carbon compounds. Right, there's a huge variety in carbon chemistry. That's what makes it unique. Now, one of the rules you must know, carbon must always have 4 bonds, unless it's some sort of intermediate, which we're not going to be dealing with in elementary organic. Always needs to have 4 bonds, okay? So those could be single bonds, double bonds, triple bonds, but you've got to have 4 bonds on your carbon atom or you've got problems, okay? So that's the rule you need to remember. Carbon's always got to have 4 bonds. Not 1, not 2, not 3, 4. Okay? So we're going to briefly talk about skeleton notation because it's going to make your life, especially as an organic student, so much better. Because when you draw Lewis structures, right, you got to draw all those C's and H's, and it just, it's pain. It's pain. It's total pain in the neck, right? Pain in the hand, too, because you got to write it all out. So if we're drawing, this is called condensed molecular notation, right? Because if we were drawing this as a Lewis structure, it'd actually be C, hydrogen, 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 C, hydrogen, 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 right? This is actually called condensed molecular notation. And even that's pain to write out. But drawing this in skeleton notation is very, very simple. And we'll talk about why it looks like a zigzag if you take 1124. The main reason is because when you make the model, it looks like a zigzag. You make the model, when we do the model kits, you'll see it looks like a zigzag. It's from the tetrahedral molecular geometry. All right, so we can condense this down into skeleton notation. And now we've represented that same 5-carbon chain really quickly. Just goes zip, 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 right? Every end and every point is a carbon with the appropriate number of hydrogens, right? So here on the end, that's a carbon with 3 hydrogens. Here's a point, so that's a carbon with 2 hydrogens. Here's a carbon with 2 hydrogens. Here's a carbon with 2 hydrogens. Here's a carbon with 3 hydrogens, right? This was a 5-carbon chain. This is a 1, 2, 3, 4, 5-carbon chain here. This takes 20 seconds to write out. This takes 2 seconds to write out. So this is what skeleton notation is. And the handout that I gave you shows skeleton notation. It's all skeleton notation because Lewis structures are a pain in the neck. So we're going to do a little bit of practice with that. Here's another one, right? So anything that's on the chain transfers as well. This is a 1, 2, 3 carbon chain with a 1 carbon chain coming off. 1, 2, 3. Carbon number 2 has a 1 carbon chain coming off. Right? So 1, 2, 3 with a 1 carbon chain coming off. Now if you'd drawn the whole thing rotated upside down, would that be a different molecule? That's just rotated. Okay, so it looks like a Y. Do we see how to do this? Long to draw, short to draw. Inconvenient to draw, convenient to draw. I'm not going to make you draw nasty molecules using skeleton notation, but I want you to have at least seen it. Do you see how we do this? Now here, we're not going to get obsessive about whether you number from the left or number from the right. There are technical rules. Now for this molecule, it doesn't matter. But there are rules for which number end you number from, which we'll get into in organic elementary. So let's try some. I'm going to put a few on the board in Lewis structure form, and you convert them into skeleton. And then we'll go the other way. Convert to skeleton. Let's see. Do that one. Do this one. And do all right, convert those into skeleton. And then these, I want you to convert to condensed molecular, just so you can have an appreciation for how big of a pain it is to do it this way. Let's do this. And I'm going to pause the recording for you to do that. All right, so let's go over these. Converting to skeleton, what's this one going to look like? It's just going to be a square, right? Because on every corner, that's a carbon with its appropriate number of hydrogens. That took 1 second to draw. That's a pain in the neck to draw, right? Those two are the same thing. That's the skeleton notation version of that. For this one, there's a double bond, right? So if we count 1, 2, 3, 4, right? We have a 1, 2, 3, 4. 1, 2. You can renumber it if that helps. You've got a double bond between 1 and 2. Carbon 3's just got 2 hydrogens on it, so nothing special. And then for this bromine, you can draw it sticking down, or you could have drawn it like this, sticking up. I would have accepted either one. Did you get those two right? All right, let's do this one. So here, let's start with this ring. How many members are in this ring? It's a 6-membered ring, right? So it's just going to look like a hexagon. And then you've got coming up 1, 2, 3, right? So 1, and then you can draw it this way or this way. It doesn't really matter. 2, 3, right? There's a 1, 2, 3. Did you get it right? More conventional way to draw that would not be with that weird angle. A more conventional way to draw it would be on the side. 1, 2, 3. All right, that's the same thing, just rotated. So it doesn't matter. If you drew that, that's fine. It's the same molecule. Those two are the same thing. All right, now let's enjoy going backwards. So delightful. All right, so if we're going to go backwards, we've got to take every point and every end and turn it into a carbon with its appropriate number of hydrogens. All right, so we've got 1, 2, 3, 4, 5. And by the way, it doesn't matter where you begin numbering on this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You're going to get the same thing no matter what. All right, so carbon, 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 carbon. Now you just need to figure out how many hydrogens go on each one. How many bonds does carbon form? 4, right? So 1, 2, 3 carbons, 3 hydrogens on that one. 1, 2 on that one. How many hydrogens are on this carbon? Just 1, right? And then 2 on this one, 2 on this one, and then 3 on this one. 2 on this one, 2 on this one, 3 on this one. All right, so I just kind of drew it on top of that. If I were turning this in for credit, I'd probably make it look a little bit neater. But I wouldn't ask you to do this because it's a pain. I might ask you to go this way, but I probably wouldn't make you go back. All right, carbon, 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 carbon. How many hydrogens are on this one with the chlorine? How many hydrogens are on the carbon with the chlorine? 1, right? And then this one gets 2. This one gets 2. How many go on this one with the double bond, both of them? Just 1. And then over here with benzene, every single one of these carbons gets how many hydrogens? Just 1, because every other bond is a double bond. Do we understand how to do this? Feel pretty good? All right. So now we're going to go through functional groups, which are on the handout that I gave you. Like I said, that's something that you'll need for organic, whether you take the full semester organic or the intro organic, either class you're learning functional groups. So let's look at the handout. A functional group is just an area of a molecule where a reaction tends to occur, right? So we can classify organic molecules by the functional groups they have, and then molecules with similar functional groups will have similar reactivities. Right, so there's the handout. That's just a copy of your handout. Okay, you've got to be able to both name and identify functional groups. Actually, I should move this out so I'm going to be able to write. I'm going to move my picture down on the screen a little bit so I can write. Okay. So an alcohol is an OH. So for instance, if I gave you this molecule and I said identify all the functional groups, right? That's an alcohol. That's an alcohol, not the carbon. No, the carbon is not part of the alcohol. It's just the OH. Okay, it's just the OH. So there's an alcohol. There's an alcohol. There's an alcohol. Okay, all of those are alcohols. The carbon that it's attached to is not part of the alcohol. It's just the OH. So if I gave you this molecule and said name, circle and name all the functional groups, right? You would circle the OH and say alcohol. Right? The OH is the alcohol. The carbon is not part of the alcohol. All right, let's talk about aldehyde. Aldehydes are always at the end of a molecule. That's key word. Why would it have to be at an end? Let's think about it. If the functional group is whatever, C double bond O H, how come there cannot be another bond coming off of here? If there is another bond coming off here, how many bonds would that give carbon? 5. Can carbon form 5 bonds? No. So an aldehyde has got to be at the end because that ends the chain right there, right? So you don't have to write that H, remember, because in skeleton notation, do you show H's? No, you're just imagining the H right there. So if I gave you this molecule and said name and identify and name all of the functional groups, right? This is an aldehyde. A lot of students forget. They'll say, oh, aldehyde is C double bond O H. Well, that's true, but there are no H's in skeleton notation. Okay, so you do not have to see an H sitting there for it to be an aldehyde. This one I did write it just so that you can see one with it and one without it. Right, that's an aldehyde as well. Is this carbon right here part of the aldehyde? No, that's just the carbon that it's attached to. Okay. So make sure you know this carbon is not part of the aldehyde. And make sure you realize that the H could or could not be shown. Okay? I wrote it here just to help you, but I don't have to show it. Okay? Now a ketone is an aldehyde without this H on it, right? It's just a C double bond O, right? So they're always on the interior of a molecule. Why do they have to be on the interior? Because can you have just this? Can you have just this? Is this bonded to anything? It's bonding to nothing, so that is unnecessary. This is bonded to nothing, so that's unnecessary. Can you have just a C double bond O floating around? No, why not? How many bonds does carbon have? It's only got 2, right? Carbon needs to have 4. So if I gave you these molecules and said, all right, what functional groups do you have? This is the ketone right there. This is the ketone right there. Now with amines, you can have a primary, a secondary, or a tertiary amine. The only difference is the number of hydrogens, right? So you can technically have just plain old N as well. I'll show you an example of one that's just plain old N, right? But there's an amine, there's an amine, there's an amine. Right, so the difference between this one and this one's a primary amine, this is a secondary amine. That's the only difference there. I wouldn't make you identify that on a test. Okay, ether. An ether is an O. It's on the interior. It's got to be on the interior because you have monatomic oxygen just floating around, right? So that's the ether. That's the ether. Okay. Ester is C double bond O O. So many students mess this one up, so make sure you don't do that. A lot of students will say, oh, that is a ketone next to an ether. That's what they'll say. They'll say, oh, this is two functional groups, a ketone and an ether. But if you see them side by side like that, that itself is a functional group. Okay? A lot of students will say, oh, there's a ketone, there's an ether, and I will mark you wrong, right? Because when they are side by side like that, that is a functional group, which we call an ester. Okay? And the same thing happens with carboxylic acid. Got to be on the end. Why? Because the chain ends here. A lot of students will say, oh, that's a ketone and an alcohol. And they'll split that up as two functional groups. And I will mark you wrong, right? Because this is not two functional groups. When you have those two side by side, it is its own functional group. That's functional group. That's functional group. We call it a carboxylic acid. Okay. So all of these are on your handout. Does everybody understand how to interpret the handout? Is everybody good on how to interpret the handout? So you need to be able to name and identify, right? So I suggest making flashcards, write alcohol on one side, and then write OH on the other side. Write aldehyde on one side and write C double bond OH on the other side. And that's what I recommend doing. Obviously, how you do it's up to you, but you've got to be able to do both, naming and identifying. So let's just look at each one of them closely. Right, there's some alcohols. There are some aldehydes, again on the end. There are some ketones. There's a carboxylic acid. There's an amine. There's ether. And then let's just do some practicing without looking at your handout. What functional group is that? Alcohol. What is this one? Ketone. The one up here is missing too. What's this next one? What's the third one? C double bond OH. Aldehyde. Okay, here's what I want you to do for here. Turn this carbon into an amine. Turn this into a carboxylic acid. Turn this into an aldehyde. Something wrong with the other one? Okay, thanks. So if I'm turning this into an amine, is it still a carbon? It's not a carbon anymore. What is it? It's now a NH2, right? In B, if I'm turning this into a carboxylic acid, that carbon still stays there, but what happens to it? It gets C what? Double bond O, OH, right? And in here, if I'm turning this carbon into an aldehyde, what happens to it? What's the difference between aldehyde and carboxylic acid? C double bond O. Is there an OH or just regular H? It's just a regular old H. See how we did that? All right, last one. Here's some amines. These are examples of tertiary amines versus the plain old N. All right. So we have amines present in caffeine. What other functional groups do we have? Which one do you recognize? It is. Is there one? There are two ketones. Good. All right, so that's where we're going to stop.